Why do we almost always find duplicates of things such as pumps, fans, and compressors in building services engineering? Why does only one of these work at a time? Why do they sometimes swap over? And what controls them? That's what we'll be covering in this video, which is kindly sponsored by Telecontrols. Telecontrols are one of the leading manufacturers in the automation industry since 1963. Their load monitors give you peace of mind when it comes to heavy-duty monitoring and utilization of pump systems. They offer protection and optimization to your equipment. Check out their load monitoring relays along with suitable relay bases and accessories. You can contact them at sales@telecontrols.com or via LinkedIn. To learn more, check out the link in the video description down below. In commercial buildings, high-rise residential, industrial plants, and utilities infrastructure, we almost always find duplicates of mechanical plant items such as pumps, fans, and compressors. The simple reason for this is that if one were to fail, the other one can take over. Take this pump set for example. This supplies water to a storage tank, which then supplies each floor. We need to ensure the water is always available. There are two pumps connected to the same pipe, but only one pump runs at a time. The pump which runs is called the duty pump. The idle pump is called the standby pump. So we have a duty and standby pump set. Depending on how critical the pumping system is, we might even find multiple standby pumps for additional safety. This also applies to fans, chillers, etc. Now, if the duty pump were to fail, we need the standby pump to take over. So, how do we control the pumps? Well, we need an alternating relay, and we'll see how and why these are used a little later in this video. Another reason for duplicate plant items is load matching. If you imagine a typical office block, it might have two sets of chillers to provide cooling. In the middle of summer, when the cooling load is the highest, both chillers and pumps operate. But in the middle of winter, the cooling load is much smaller, so one chiller and one pump operate. Therefore, we might need the standby set to also provide support if the duty set cannot cope by itself. We can also save a lot of energy by running pumps and fans at the same time, making use of the fan affinity laws, but we won't cover that in this video. This pump fills a storage tank. It's controlled by a float switch. When the water level drops too low, the float switch triggers a relay which starts the pump. When the water level is high enough, the relay cuts the power to the pump. By the way, we have covered how relays work in detail in our previous video. I'll leave a link in the video description for that. Now, this pump and relay work well. However, if the pump breaks, there is no backup, so the entire system will be out of service until the pump can be repaired or replaced. That's an easy problem to solve though. We just install a second pump and control the two with an alternator relay. Now, when the duty pump fails, the relay cuts the power and changes over to the standby pump. The problem we now face is that if the standby pump hasn't operated in a long time, the bearings will have seized and the internal parts might have rusted, so the backup pump will not be able to start. To stop this from happening, we can alternate the control of the pumps so that they take turns. The pumps will then have nearly equal run hours and the wear will also be equal. Here we have a simple schematic of an alternating relay circuit, which is controlling two compressors. The pressure transducer is connected to the common wire of the relay, which feeds the compressors. The relay controls a switch which diverts the flow of electricity. We will look at what happens inside the alternating relay a little bit later in this video. As the pressure in a compressed air system falls, the pressure transducer closes and completes the circuit. Electricity can then run through contactor 1, which turns on compressor 1. The alternating relay does not energize, it does not operate, and it does not change at this point. When the pressure in the system increases to a satisfactory level, the pressure transducer opens and cuts the power to the compressor. Now the alternating relay can change position. When the pressure drops again, the relay is diverting power to compressor 2, and this time compressor 1 is off. When the system pressure builds up again, the transducer opens. Compressor 2 will stop and the alternating relay changes back. Each time the transducer opens, the alternating relay flips to the other set of contacts. This ensures that each compressor runs for an equal number of hours and that the wear on the components are the same. The compressors will therefore swap from the duty and standby role each time they are called to run. Here we have a diagram of a simplified alternating relay circuit. It might look complex, but don't worry, we're going to go through this step by step. We have 3 solenoids and 10 switches. These control the 2 fans and alternate them. Switch 1 is the main switch that turns the entire circuit on and off. Switches 1, 4 and 8 are interlocked with solenoid 1. Switches 2, 5 and 7 are interlocked with solenoid 2. And switches 3, 6 and 9 are interlocked with solenoid 3. When current flows through a solenoid, it generates a magnetic field. This pulls the connected switches and they change position. We have covered how solenoids work and even made our own version in our previous video. Do check that out, links can be found in the video description down below. Currently, the main switch is open, so the fans are off. When the main switch is closed, current can flow through switches 3 and 2. This energizes solenoid 1 and fan 1 also turns on. As solenoid 1 has energized, this causes switch 1 and 8 to close and switch 4 opens. The current now flows through switches 8 and 7 and through solenoid 3. Solenoid 3 energizes. This closes switch 9 and 6 and opens switch 3. Fan 1 therefore continues to run as the current now flows through switches 1 and 2. When the main switch opens, the current stops flowing through switches 1 and 2. Solenoid 1 de-energizes and fan 1 stops. As solenoid 1 has de-energized, switches 8 and 1 open and switch 4 closes. Current still flows through switches 9 and 7 and also solenoid 3, which keeps switches 3, 6 and 9 in position. When the main switch closes again, the current passes through switches 6 and 4 to solenoid 2, and so fan 2 runs. As solenoid 2 is energized, switches 2 and 7 open and switch 5 closes. The current to solenoid 3 is cut, causing switches 9 and 6 to open and switch 3 closes. Fan 2 continues to run. When the fan is no longer required, the main switch opens. This cuts the power to fan 2 and it turns off. There is no current to solenoid 2, so fan 2 stops. Solenoid 2 is de-energized, causing switches 2 and 7 to close and 5 to open. Both fans are now off. So that's how we can switch between loads using solenoid coils and switches. But to make it much easier, we can just use an alternating relay to do this for us. Sometimes we need to run both pumps, fans or compressors at the same time. For example, with a set of air compressors, if the demand for air is very high, then 2 compressors might need to run to meet the demand. For this, we can use lead and lag sensors. The lead sensor detects the initial decrease in pressure and tells the duty compressor to start. If the pressure then continues to decrease, the low level or lag sensor tells the standby compressor to also start. Let's see how this works using a simplified diagram. If it looks confusing, don't worry, we'll go through it step by step. First, we have the lead and lag pressure transducer switches. Then we have 2 electrical motors for the compressor, but they could also be for a pump, a fan, etc. We also have switches 1 and 2, which are normally open. These are controlled by the solenoids 1, 2, 3 and 4. We also have an alternator relay which controls the interlock switches. Initially, Both the lead and lag pressure transducers are open, and both motors are off. When the lead switch closes, motor 1 turns on. Solenoid 4 is energized and closes switch 2. This also energizes solenoid 3. If the pressure continues to drop, the lag switch closes and motor 2 also turns on. Solenoid 2 causes switch 1 to also close. This will then energize solenoid 1. When the lag transducer is satisfied, it opens the switch, but both compressors will continue to run. We want both motors to continue to operate. This will ensure the demand for air is satisfied, because we know that one compressor alone wasn't enough to satisfy the demand. If we didn't keep both motors running, then the standby motor might continuously turn on and off. This will damage the electrical motor and eventually destroy it. When the lead switch is satisfied, it opens and both motors turn off. Switches 1 and 2 open, and the alternating relay changes position to change the duty and standby over. Now, when the lead switch is closed, motor 2 turns on. Solenoid 2 closes switch 1, and then solenoid 1 turns on. When the lag switch closes, motor 1 turns on. Solenoid 4 will close switch 2, which also energizes solenoid 3. When the lag switch opens, solenoid 4 turns off, but motor 1 continues to run. When the lead switch opens, both motors will turn off. Switches 1 and 2 reset, and the alternator relay changes the lead and standby positions. This is a simplified example to help visualize how it works, but the modern alternating relay will use solid-state electronics and will have many additional functions such as maintenance override, time on and time off delay features, as well as automatic fault changeover. Okay, that's it for this video, but you can continue to learn about electrical and controls engineering by clicking on one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, and of course, theengineeringmindset.com.